My name is Mariam Falohpour, and today with Dr. Alan Simmons, we are going to talk about some of the commonly used pre-processing steps for functional MRI. I would like to start with a very easy question. Why should we pre-process the data? Well, for most studies, we start with study design, then we collect the data, then we do cleaning the data or removing the noise, and I made this box a bit bigger because that's what we are going to talk about today. Then we do some sort of statistical analysis, interpreting the results, and if the results make sense, we write a paper or a new grant, and then we will be happy. So if we make mistake in any of these steps, we may not actually get to the end that to reach our goals. Today again, our focus is actually to see how we can clean the data. But first, we have to answer this question: what is noise? So if you're talking about denoising, what exactly we mean? This question is not easy to answer in this field, mainly because it's actually what is a signal of interest for one study might be considered as noise in a different study. So in order to actually clean your data, you have to understand the goals of your study and make sure that actually what you're removing is noise. So this is actually a very general comment. However, for many studies in this field, we are interested to understand how brain works, and we are interested to actually work on the data that is related to neural activation, and anything that is not related to the to neural activation is kind of considered as noise. But again, for each study, it's better to actually understand what the goals are, and then that would be easier. That would make it easier later to actually decide about the denoising approaches. So let me start with a toy example. I made this time series myself, and just assume that they are a time series from 3 random voxels in the brain, V1, V2, and V3. If you look at the first row, this is actually the original time series, and the relation between V1 and V2 is actually not significant at all. But between V2 and V3, there is a strong negative correlation, meaning that they actually go up and down in reverse order. If you look at the second row, I added some low frequency fluctuations to all three of them to different extents. And as you can see, if you look at the new correlation values, I have some positive correlation between V1 and V2, and now it's significant. And between V2 and V3, it became less negative. In the third row, I changed the intensity of the first few reps. And again, kind of the correlation between V1 and V2 increased even more, and between V2 and V3 is actually not significant anymore. And in the last row, I actually added a few outliers in the middle of the time series. Now, if you look at the how these values changed, so the relation between V1 and V2 actually changed from being not significant at all to something really positive and strongly significant, whereas between V2 and V3 it started with very negative and strong negative correlation and ended up being positive and significant correlation. So what I did here actually, the noises that I added to these time series, they are not far from reality. They are actually scenarios that are very probable in fMRI data, and it actually, if you look at raw fMRI data, you'll see, you may see actually all of these three cases at the same time. So again, that makes it hard for actually finding the true relation between given voxels. For this example, I knew what the ground truth is because basically I made them. But in reality, we don't really know what the true relationship between these time series are, and that true relationship can easily get masked by different sources of noise. So I just wanted to emphasize this at the beginning, so we can be more careful about what we are doing with the data and how we are doing the pre-processing steps, because even sometimes we can artificially induce some actually relations between different voxels if we and basically kind of masking the true relationship between them. So having said that, now I would like to actually switch gears toward just talking about some of the commonly used pre-processing steps in this field. I would like to start with the distortion correction. So the inhomogeneities in the B0 magnetic field causes distortions in the fMRI data. So there are some approaches to basically correct for these geometric distortions. So for each subject within the scan, we can collect some additional scans, like by, for example, collecting a field map, or by collecting some blip up, blip down pairs, basically just collecting data in different phase encoding directions. There are algorithms to correct for this geometric distortion. So one thing to note that is that basically to be aware of this distortion and think about it ahead of time. If the area that you're interested in is close to the area that are actually these distortions are more severe. So if you're interested in areas that are basically on the frontal area, so these distortions, let me say this first, that are worse in the areas that are filled with air, like around sinuses. So if you're interested to study regions close to that, then you probably have to change your imaging parameters to be able to basically minimize the distortion in that area. But this step actually overall is actually very helpful when you want to later on do the registration, or if you want to transfer your data to a standard template, because basically most algorithms assume that the shape of the brain is like a brain, is not stretched or squeezed on the front or somewhere else. So this is a helpful step for later on for registration. The next step is slice timing correction. So when we think about fMRI data is like a four-dimensional data set. So we have a volume and we have time. So the fourth dimension is the time. And kind of we assume that the entire volume is collected at the same time. So this assumption is not true for many imaging sequences, and mostly the imaging sequences which are used for functional MRI data are actually collecting the data slice by slice. And there are commonly used approaches for actually common ways of actually collecting the data is either you can do it sequentially or in interleaved manner. So for sequentially, you basically start from slice 1, 2, 3, 4, and so on. But if you are going to use interleaved manner, basically you collect, like, let's say, even slices first and odd slices later. So this is kind of, these slides show you how the interleaved acquisition is going to be. So this is the case for single band acquisition. But if you are actually using multi-band acquisition, you're actually collecting multiple slices at the same time. Let's say in this example, the multi-band factor is 3, and each time we are collecting 3 slices basically. So again, this is showing the collecting slices in interleaved fashion. So the problem with slice timing differences in the timing of the acquisition for different slices is that basically let's assume that you have, for example, 5 slices, and assume that there is an activation and a hemodynamic response function for these 5 slices are identical. But if there is a difference in the time of the acquisition for these slices, if you look at these red dots here, so the time that we are acquiring a slice 4 to 5, actually the amplitude of the that signal is going to be different from one to another, even though they had the identical response function. So what we collect is actually in the bottom row. So what we need to do is actually finding a reference slice and then align all the other slices to that reference slice, such that we actually as if we collected all of them at the same time. So in order to do that, we have to interpolate the time points that are missing. So for example, on the right figure, if you look at the blue curve, it's what is originally collected, let's say at time 0 to 4 and so on. But we are going to find align it to a slice which is like the middle slice, let's say, which is collected at time 1, 3, 5, and so on. So this figure is actually shows the linear interpolation, but there are other algorithms to find actually to do the interpolation. Basically, you can use sync, spline, or other algorithms basically. So if you're doing resting state, this is that's where you have to do the slice timing correction. But if you're in your study, you're having a task, then you can actually model these slice timing differences in your GLM by adding the derivatives, for example. One thing to point out, however, is that as the actually the as the actually we are getting better in terms of data acquisition, and the TRs are actually decreasing, the time difference between the acquisition of the very first slice and the very last slice is reducing. So let's say maybe 10 years ago, the TR was in the order of 2 to 3 seconds, but now we are using multi-band imaging techniques. We can collect the whole volume in, let's say, about 700 to 800 milliseconds, meaning that there is not much big difference between the time of the acquisition from the first slice to the last slice. So having said that, given that the bold response is slow, maybe this step may not be an issue in future at all, or many studies actually skip this step. So it really depends on the goals of this study and the scanning parameters, whether you want to include the slice timing correction in as your pre-processing steps or not. You have to actually think about it, and based on your data acquisition parameters and again the goals of your study. The next thing that almost everyone or many studies actually do include in their pre-processing steps is the motion correction. So motion is one of the issues in the fMRI data that there's still not actually a solid good solution for it yet. So let me start actually by showing you these movies. I kind of like them, and I found them actually from that link below. So they are just showing the how the head moves, and the the amount of motion in the bottom row. If I go to the next slide, this is a bit slow. Okay, and these are the rotation parameters. So as you can see, as subject's head moves, the location of the voxels obviously are not the same as before. So that's the so when there is a motion involved, and there are two big issues. First is the displacement of the voxels, and the second is actually changes in the signal intensity. So the changes in the bold response due to neural activation is really tiny. It's in the order of a few percent. And the changes due to motion can easily mask that. Let's assume you have two neighboring voxels with different intensities, and let's say your resolution is 3 millimeter. So if the subject moves by only like a few tenths of a millimeter, like let's say 10% of a voxel size, like 0.3 millimeters, then there is going to be 10% change in the time series, and this can be much larger than the changes in the signal due to neural activation. So motion, again, it's not easy to deal with, but what we can do, actually what most algorithms do, is let me go to the next slide. Let me go over this first. So this is another movie from the same website, just showing the data just by visually inspecting the data before and after motion correction. And for subjects who move a lot, actually, you can obviously see that if you put it in the movie mode, you can obviously see the motion in the movie mode. Um, so, okay, going back to the volume registration and motion correction. So the way that people do is that you find, you actually decide about a reference, select a reference volume, and then align all the other volumes to this reference volume. And once you do that, we usually most algorithms use rigid body transformation, meaning that there are 3 translations and 3 rotations. So you end up having 6 time series um, after doing the alignments. So these are very useful time series because you can use them later on to basically clean up your data to some extent, and also use some metrics that use these time series to actually determine how much motion is in each volume, for example. So one metric that I put here is called frame-wise displacement, which is actually showing the motion frame by frame in millimeter. So you can use that again later on to somehow censor your data if you want to. This is also another plot just showing that even after removing the motion parameters from the time series, so basically cleaning the data, we can still see high correlation between the percent change in bold and the FD measure. So if you look at the 3rd row and the 4th row, you can see that the peaks are aligned. So even after motion regression, the data is not completely clean and there are some leftovers in the data. This is also another plot showing that how motion is affecting the signal intensity in the entire brain. So if you're not familiar with these plots, let me just quickly go over them. So your x-axis in these gray plots, your x-axis is time, and your y-axis is the number of voxels. So each tiny line is a time series for a voxel, and the intensities are actually there's a color bar here, goes from -2 to 2. So basically the intensities of the time series is scaled to that color bar. So this plot shows that if you look at where the purple arrows are, and those are when the subject has moved and the head motion has a peak, and if you look at the data, and there is a significant change in the signal intensity in all gray matter, and partially goes to white matter and CSF as well. Whereas in the blue arrows, there is like a peak in the motion, but the effect in the bold time series is not as strong. So this is just to show that the way that actually motion affects bold time series is not easy. It's like there's a complicated pattern in there because there is a spin history, and there is like changes in the magnetic field as the motion as the subject moves. So meaning that, so just be aware of it, that motion does not have a simple effect on the data that we can characterize like only by actually looking at the regressors. Just be aware of it. The next thing is spatial smoothing. So, spatial smoothing generally increases the SNR by reducing the high frequency noise in the data. So what it does is kind of computes the weighted average of the neighboring voxels with different weights and replaces each voxel by actually its the weighted average of the neighboring voxels. So uh, the operation actually just getting kind of the operation makes the image blurrier and basically reducing the effective resolution. So um, so there's a trade-off between how much you want to actually spatially smooth your data. So let me actually before going talking about how much you want to smooth, explain what FWHM is. So if you want to use like a Gaussian kernel for, it's very common to use Gaussian kernel for smoothing, and it's defined and it is defined by something called a full width half maximum. So which means that at the half of its maximum value, what the width of the curve is in millimeters, the wider the wider it is, meaning that you're including more neighboring voxels for averaging, and the narrower it is, it means fewer voxels are included. So if you want to be conservative, you pick like a thinner kernel, and if you want to smooth more, you pick like a wider kernel. So overall, again, as the size of as FWHM increases, basically the image gets blurrier and blurrier. So the amount of smoothness really depends on your data and what you're looking for in the data. So if the size of your the area that you're interested in to study, and you know that the size of activation is large, then it's okay to use a large kernel, and it will actually help you to some extent. However, if you're looking for a tiny area, then using a large kernel would not be useful at all, and actually it may actually increasing the actual size of the kernel, you may not be able to see activation in the small area that you're interested in. You can actually see it in this figure in the bottom row, that these the large areas on the occipital on the kind of, because it was many voxels had kind of the same activation. As you increase the smoothness, they kind of merge. Whereas assume that like one of those tiny dots on the frontals, if it was real, and you were interested to actually study those, then as you increase the size of the kernel, those areas are gone. So this is again a trade-off between the size of the activation and how much your data is noisy. But as a general rule of thumb, maybe about twice your voxel size would be a good place to start with. The next step is actually spatial normalization, or transferring your data to standard space. So if you're going to do any sort of group analysis at the end of your study, then you have to normalize your individual data to some standard template. There are different ways of doing the normalization, and I think like probably for many studies the two-step normalization is what many people use, and Chris talked about actually this part like on last week, so I'm not going to spend so much time on this slide. The next thing is detrending your data. So if you look at raw fMRI data, even if the data is from a phantom, you will see those low frequency drifts in the time series, and these drifts may go up, may go down. Sometimes there is a little curvature to it, but in overall, they are kind of again in the low frequency domain, and they are actually known to be related to scanner imperfection and the problems in the hardware. The electronics, the wires, they heat up, and it's actually believed that they are causing these low frequency drifts in the time series. In order to remove them, if you're using a model-based approach, you can model these low frequency artifacts using some low-order polynomials, or you can use the DCT basis sets. But again, you can model this in your data. One thing that I would actually like to repeat here is that something like low frequency drift, which again for many studies are considered as noise, it might be the signal of interest for some studies. For example, if there is a study that looking at the effect of some drugs, there might be changes in the brain state over time during the scan time, so which may cause like a drift in the time series. So just wanted to actually emphasize again that the goals of the study matter. So the signal, as obvious as linear trends, which again is considered as noise for many studies, might be the signal of interest for some other studies. Just again be aware of this. The next thing is physiological noise. So, and mainly what I'm going to talk about now is the effect of respiration and cardiac on the fMRI data. So, respiration and cardiac generally, we can say they affect the both signal in two different ways. So the first way, which is directly related to the pulsations and the breathing, is aliased in the time series, in the fMRI time series. And what I mean by, if you're not familiar with the term aliased, meaning that it means that if you have some fluctuations, let's say the very first row, if you look at the very first row, there are some fluctuations. Let's say this is breathing. If you don't sample fast enough, if you look at the second row, the red dots are where, let's say, we sample the data. Then what we are going to see is actually that red curve, which has only one cycle. So the original time series had many cycles here. I don't know how many, maybe 20, whereas what I sampled looks like one cycle. So this is called like aliasing, meaning that some high frequency effect is actually mapped to very low frequency because of undersampling. But if we sample fast enough, then this issue aliasing will not happen. So if you look at the third row, so if you sample at least 2 samples per cycle, then you're okay actually. So again, like for example, if you want to talk about the cardiac, the heart beats like about 60 beats per minute, so about 1 hertz. And if you want to be sampling fast enough, we have to go actually collect the fMRI data, let's say in at least twice as fast as 1 hertz, meaning that we have to be able to collect the entire volume in less than 500 milliseconds. So as the advancements again in the imaging sequences and using the multi-band sequences, these are actually aliasing in the fMRI data may actually go away soon in like a near future. But it was more severe again when the TR was much longer. But there are approaches actually that can take care of it and reduce their effect in the data. And retro-ICOR is one method for reducing the effect of alias physiological noise in the data. So basically what it does, it reshuffles the data based on the phase of the cardiac and respiratory cycle, and then tries to fit that to some low-order Fourier transforms. So that's the first effect of the changes in the basically the effect of respiration and cardiac on the fMRI data. The second effect, it's inherently low frequency, meaning that if there is a change in the respiration pattern, like if the depth of the respiration is changing, that will modulate the CO2 in the blood, which is known to be a vasodilator, and the changes in the CO2 was shown in the brain was shown that was actually in low frequency range, like maybe around 0.05 hertz. So in order to model that effect in the data, there were again some approaches. One of the very first papers that came out was using the RVT regressors, and RVT is defined as respiratory volume per time. So it looks at the peaks and valleys of the respiration time series over one cycle. And then if you regress that from the data, it was shown that it can get rid of part of that noise from the data. But there were again some other works that kind of completed that RVT approach, and they introduced response functions for both heart rate, changes in the heart rate, and also changes in the respiration pattern. And so basically they introduce cardiac response function and respiratory response function. And what it means is that the changes in the respiration volume affects the both data through some response functions, like kind of like impulse response function. So if you convolve them together, that's what you can use as a regressor in your model-based approach, and to reduce the effect of physiological noise. But if you don't have reducing the effect of physiological noise, using the approaches that I mentioned requires some external recording. There are other approaches that do not require external recordings, and they are actually using the tissue signals. And what I mean by tissue signals is non-gray matter tissue signals. So the assumption behind these approaches is that we are mainly interested to study the gray matter because, again, our assumption is that mainly the neural activation and what we're interested in happens in the gray matter. So therefore, we can use the other tissues like white matter, large vessels, large ventricles signal, and assume that these time series actually they have information about other types of artifacts in the data, and we can actually use it in our model-based approach and use them as regressors in the model. So an anti-core is one of them, one of these approaches, and then COMP-core, which again, like it's very similar to the other one. They just get the principal components of the tissue time series. So one thing to point out, which is very important here, is when we talk about the tissue signal, let's say CSF or white matter or large ventricles, we have to make sure that the masks are defined very conservatively and very carefully, because even if there is like even a little bit of overlap between the tissue mask and the gray matter area, then then it's gonna be like actually similar to using global signal or gray matter signal. I haven't talked about global signal yet, but just wanted to point this out here because it's important. If you're going to go for approaches like this, be very careful about how you're defining your masks, because again, even if you have a few hundred voxels in your white matter mask, with the overlap with the partial volume with gray matter, then it's gonna be very similar to actually using either gray matter or global signal in your model. So be very careful about it. The next thing is actually global signal regression, or basically including the global signal in your model. Global signal is defined as the average of the time series, the all time series in the brain. And it's been shown that if you include, and the idea is that basically it actually represents something which is global, and that's not how brain works. And so therefore we can use global signal and assume that it mainly contains signals of no interest. It can mainly contains probably the leftovers from physiological changes or scanner artifact, and so we can include that in your model, because we are mainly interested in more localized activations. Well, to some extent, this assumption is true, but it's not 100% true. So here, I'm not going to actually, so including the global signal is still under debate, and many labs do it, many labs don't do it, and don't think it's a good thing. But again, I don't want to go into details about whether it's a good thing or bad thing, but I just want to raise awareness and let you know that if you're doing it, just be aware that it 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 also contains neural information, like the plot bot in the second row. It shows the correlation between the global signal and the EEG vigilance, which was found to be relatively very robust, and actually across different sessions and different subjects, it was shown to be negatively correlated. So meaning that it has, if you're including global signal in your model, be aware that you're also removing some neural activation from your data. You may benefit from actually getting rid of some global effects in your data, but on the other hand, you're also removing some neural activation. So again, I wanted to just I don't want to go into details about the pros and cons of using it. Just wanted to again remind you that that you have to think about the goals of your study, and try to understand if the step that you're doing makes sense for your data. So after you defined all those regressors that you want to remove from your data, like including the motion regressors, the physiological, if you have tissue signal and maybe global signal, then you can form a GLM. And basically, if there's a task involved, you'll have a design matrix, and then you have your noise matrix, and you can fit that model and solve for to find solve this equation to find basically your beta values. If you have resting state, then you probably don't have the design matrix, so you can just form your noise matrix and use this equation to clean up your data. So your residual error is actually your clean data that you can use if you want to do some other you want to apply any other algorithm to it, then you can work on that. There are, so this is like a model based approach, and assuming that we assume that there is a linear relation between these terms, and we have some, again, recordings, and or maybe not, and we are just using tissue signal, but again we are assuming some relationship and some model for the data. There are some other approaches that they actually don't assume this model and let the algorithm decide, and they are more data driven approaches, and one of the most commonly used methods is called independent component analysis, or ICA. So if you use ICA on your data, it basically gives you a bunch of independent components, or ICs, spatial maps, that you can actually, along with, for each map there is a time series that shows the weights for that given map over time. And you can, for each component, you have to decide whether that component is a noise or a signal of interest. So here I have a few examples, and that again, for each component you have to either manually give it to like an expert to decide whether each component, again, is noise or not noise. So there are some automatic algorithms that can do that for you, but again, you have to trust the algorithm. So for example, in this plot, the top left, it's kind of the activation is on the edges, so it looks like to be like related to motion. And whereas if you look at the bottom row, right, and the right bottom, the last row, it looks more like a default mode network. You can use the information from, I mean, you can look at the spatial maps, of course, and you can also look at the time series and the spectrum, and all collect all that information and then make a decision. So if you want to be but again, it's like the expert's decision to either keep or remove each component. So I mentioned again some of the steps that people use for cleaning the data, and for each of those steps there are several parameters, or there are several things that you have to think about and make decision about. And also I didn't actually mention any about like the order of these steps, so which one has to be done first, which one can go next. So if there was a paper actually which looked at the possible ways of processing the data, and I believe it's the possible way is only using the FSL. And it's interesting that if you just do the math, and they find that there are about 70,000 different ways of processing the data, which is really a huge number. And again, I believe this is only using the FSL option. So if you add the other packages, the number would be even larger than that. There's also this paper which they actually looked at 241 papers from highly ranked journals, and out of 241 studies they found 223 unique pipelines, which is amazing, meaning that there are as many pipelines as the number of studies. So this is probably not a good thing, because that much flexibility actually makes it difficult to sometimes to reproduce the results, and also gives rise to false positive. So yeah, so in the same paper they actually looked at which steps were done most, or basically the percentage of the time that each step was used. So if you look at the purple bars, it's for pre-processing, and you can see like how many studies actually included, for example, motion correction in their pipeline. So this is actually very interesting to know that like many studies did include the motion correction, normalization, spatial smoothing, whereas like, for example, slice timing correction was like done about like 50% or so. And this is again another plot showing about actually how the results were reported, which is kind of related but not directly. So it's important to not only using different pipelines, but the way that different groups report. Actually, there were differences between them, and some studies do not report in details, which is also another like a separate issue. There are also some studies that actually looked at the order of the pre-processing steps. For example, this work used simulation to simulate the data to actually show that look at the effect of actually filtering and censoring the bad time points. So if you have like a outlier or bad time points in your time series, and if you keep it in the data and do the filtering, that the effect of that bad time point actually propagates in time, so it makes more time points contaminated. So it's better to actually get rid of that bad time point and interpolate it, and then do the filtering. There's also like this work which looked at the actually what's the best order when you want to do retro core motion correction and slice timing correction. So they found that for both high resolution and low resolution images, doing retro core first and then time shift correction at the end, it actually helps. It's probably better. So there has been some work on finding the right order of processing the data, but not all different combinations have been studied yet. So that actually gives us motivates us actually to maybe use more standard approaches and use the pipelines that were developed by people who have been in the field maybe longer than us, and had thought about some of these issues. So with that, I'm going to actually ask Alan to come and talk about AFNI-Proc.
So we're going to be also covering how this processing pipeline is handled within AFNI. So the functions that need to be done as part of data cleaning that were addressed by Miriam are handled within the AFNI system. So I'm going to walk through interacting with AFNI ProcPy and what its primary duties are and primary considerations in dealing with your pre-processing of your data. We're going to break out the pre-processing mostly today, and we'll handle regression mostly in a upcoming lecture. So the AFNI ProcPy is not so much a script that runs things, but a script that creates a script that runs things. And if you want to get even more meta than that, Uber subject.py is a GUI interface which creates an AFNI ProcPy for you to then create a proc file. So even more levels. So the Uber subject is not something that you will want to regularly work with, but is a nice way of walking through if you want to get some initial familiarity. AFNI ProcPy will also give you some QA results that you'll work through. So, as stated, the pipeline that you select, you can go either through the Uber subject, or you can really go through the examples. And the examples are a nice starting place, and you can adapt those over time as you learn a little bit more about AFNI, a little bit more about what things it does well and what things you want to address in different ways. So what we have here is an example of a task-based use of AFNI ProcPy. This is example number 6. There's a number of examples you can use, and if you just grep that file, you can see a nice long list of different examples and how and why you'd like to go about them. If you pipe it through the help through less, and you can search for example 6, it'll give you some descriptions of the things that are specific to this example at the header when you're going through the help, but I'm just going to focus on the text of that example. In this one, I'm going to focus really on the first 2 lines primarily. First line, you're identifying which the subject is, you're identifying what the anatomical is, and you're defining what the functional run is. The next line, you're defining what things you're going to do in your blocks. Your blocks are activities that you're going to be doing. Those will be specified in the following lines if you're going to do specific things that are outside of the default, specific things that are required to really enact what you want to do in your processing pipeline. Here we've got your T-shift and line and etc. that are bolded through there about steps you'll be engaging in. When you run this processing, this Python script, you will get an output data. That will be your proc. If it can find all the data that it needs to do that, it will give you that example proc file. That, walking through that will show you the explicit command line tools used in AFNI. And really getting into that is beyond the scope of what we're covering here today. So I wanted to say that once you've got this proc file and you run this proc file, you will get some output. This is an example of getting it all through the deconvolution. If once you start doing the deconvolutions, you'll also get a stats file out. But again, we'll be handling that more specifically in following days. Here you can see the kind of file that you'll get out and the block that was used to create that file. Here we have processing block 00. That is one that's an automatic block, that TCAT block. What its job is to do is to concatenate your file, but also to take off the first two TRs by default. You can change that number if it's already been dropped, but if you're using a GE scanner, you'll want to cut those before you start doing things like working out your out count, working out and inferring things from your dspike and time shift. So the dspike is the next step that was done sequentially on this set of data. The dspike is an optional block, but is very important. And you can walk through the rest of this. The first block is the processing. The second block is output texts. And the last block that are started with these ampersands are functions. You run these and it will walk you through QA on your data. And these can be very helpful to make sure that you look at all the important things of your data as you go through it. I want to touch here on one of the earlier steps of our sequence is the tail rocking. The large part of the pre-processing is taking care of spatial concerns. The large part is taking care of temporal concerns. The temporal concerns will be taken care of through volume registration, dspike, dshift. The spatial concerns, moving your data into the universal coordinates like NMI coordinates, will be done through Taylor arc. It'll be done through alignment and volume registration. So moving our anatomical to M&I space can be done through SS Warper. The SS Warper will do a nonlinear transformation, and you'll remember back when Kristen talked about different kinds of warping, FSL and through AFNI, of things that you want to do to your anatomical. And here, the application of your anatomical to the M&I space can be done through this pipeline. Here we'll be doing unifies, which is the N3. Like an N3 correction, it's taking care of field homogeneities. So you can map white matter to white matter, gray matter to gray matter. We'll also apply various forms of skull stripped, which will be removing the data based on trying to find the surface of the brain and working our way through that. Then we'll have outputs, which will be actually the warping and the warping files. These warping output files are both useful for getting your now normalized or moved into M&I space for your anatomical, but also the path in which it was taken to get there. Those will be then utilized within your ProcPy. So if you're just doing a linear alignment, you can just leave a tail arc as is. You might want to specify a specific base if you want to move it in my. If you want to do a nonlinear transformation within your ProcPy, you can do that, and that's shown right there. This can be a little bit more intensive as you will be running this each time you run your ProcPy, and it is a long, tedious step. So if you want to use your SS Warper first and then just apply those transformations of moving your epi forward, then you can do that, and that's the one provided below using the SS Warper. So that step can be done before you do your ProcPy. The following steps are ones which will be applied on your ProcPy. Once you have your proc up, you might want to make a universal one, and this is just saying that that can be done. By default, you put in a subject and it'll make a new proc file for that subject, and you will have a proc file per subject, but it can be modified by replacing that subject variable with a specific variable that's specified, and then you can run it in loop, which can save you a decent amount of headache. I'm going to walk through the default blocks, and then the optional blocks, and then the really optional blocks. There are some blocks which are considered optional within AFNI, which you really will want to include the vast majority of the time. But walking through the default blocks, we've got T-shift, vol-reg, blur, mask, and I'm going to step through what these give you in specific. We're going to again leave the regression step for another day. Time shift, as Miriam presented in more detail, is the way in which you can go through your data and take what's given you spatially and correct for the fact that that spatial information was scattered over time. So up top, you can see the way the brain is presented is as though everything was collected at the same time, but in truth, it's been collected with a delayed lag over time, and you need to T-shift if your data has been collected in that regard. Here on our single band scanning, we do an Alt+C. That should be recorded in the header. If it isn't, then you can specify that as a parameter in your time shift options. So to go into this in just a touch more detail, what you're doing in your time shifting is if you're doing linear interpolation, you're taking a little bit of information from time 1, a little bit of information from time 0 to recreate what the data is looking like at time 1. So you're taking this is a linear example where you're taking differential proportion. The way in which you'll be doing this is actually spreading out over a broader period of time to get a more accurate interpolation of that data point, because you will never actually collect your data all burn at once at that time point. As the TR, like Miriam said, as the TRs increase, you will get closer to collecting more of the brain. It's in a smaller window of time, and the concerns maybe will reduce in that regard. Volume registration is the turning of your functional brain to make up for the fact that you're acquiring it over a large period of time. That large period of time may lead people to do things like shift their head, sneeze, turn, anything like that. And that's both going to affect the noise and the signal that you're getting out, but it's also going to affect the actual placement of a brain. So when you talk about your insula is not at a fixed coordinate over time. You'll want to fix that coordinate, and volume registration does a nice job at that. You can, with a volume registration, you're shifting the functional brains to all be map onto the same space. You can align it to any location within that space. Here, the minimum outlier is a nice default, because the less you shift your data, the less interpolation you're going to require to do. So the minimum outlier is an example of a time point where you're not bringing up too much chance of over-interpolating and over-moving your data. But there are other choices in which you can mark to. And here, the actual guts of this is done within align epi to a nat, a Python script. A lot of the help and a lot of the things and the features that you'll be applying in there, you can look up in that Python script to make sure that you're doing it as you wish. Blur, this is a interesting step. We'll talk about this a lot more on the clustering day. The blurring is a Gaussian blur that you apply to your data to increase the spatial smoothing. It takes out bullet spikes in the local data. It makes up a little bit for people's brains being in slightly different locations, the activation of in the brain being slightly different locations. You can map that through to a singular to adjacent spots a little bit better if you put some blur to it. You can either blur by an amount, like 4 milliliters, or you can blur up to a certain amount. And blurring to, you want to make sure that your blur side is more than your actual inherent blur in your data, or else you're not actually going to be doing any form of blurring. But again, we'll talk about blurring in more detail when we get to clustering. Quickly, masking. The masking step, this is to create to use a brain mask to drop things from outside the brain, but you can also use it as far as inserting. It'll be the block which you handle inserting masks of ventricles or things like that you might want to use as a noise regressor. Scaling is shifting the scale and warp the data so that when you put it into your regression, the beta weight will be a percent signal change. It's a nice feature if you're going to end up wanting to work with percent signal change. Regression, again, is a way of moving your time series data to a beta weight, and we'll handle that more in an upcoming lecture. These optional blocks are optional, but some of them can be very useful. The line is definitely one which you will want to use, as is despike. And the line will be aligning an epi to your mat. Your despike is taking out that places data, and your tailor arc is then warping you're warping your nat and referencing warping your nat to your standard space. So how does despike work? Despike, when we looked at mean outliers before and the outlier file, despike works a lot within that regard. It looks at the absolute value of the deviation, and it marks things that are outside that and interpolates the data that is marked as a outlier. So despike is excellent for bad data, and it will not harm good data. The align epi to a nat is again handled by that align epi to a nat.py that we referenced earlier, and you do it before the tailor arcing knowledge, where you start combining up all your different features with new blocks. So here's some common features that you'll want to consider is adjusting the cost function of your alignment. Here, the default is a Pearson's correlation plus CZ, which is including lots of working out the best fit of a couple different correlations. Sometimes the mutual information can give you a less precise on some subjects, but a more universally working version. Tailor arc. Here, this is after the volume registration, and this one you can specify what base, and you can either do the warping, or you be referencing functions of warping that you did before, like we did with the SS4. Some optional blocks to consider is retro iCore and the surf ones, but retro iCore can be helpful for ways of controlling signal as an core, as well as ways of controlling signals that are going to be errored in your data due to physiological aspects. So some quick considerations. You want to visually inspect your data at all times. Those automatic functions that are provided are nice ways of getting that visual inspections. You want to review all of your automatic QAs, and your interactive QAs. And as you're building this, you'll really want to consider how good your alignment is, how good your sensors are, how you're working up your regressors, and what you're deciding to include in your sample after you've gone through all your QA steps. To sort of get further into some of these aspects, there's a couple of different ones that are specific to Athene, but there's also some really good ones, largely looking at resting state data, but doing a good consideration of how things you could consider in noise reduction and pre-processing steps in your data. Thank you very much.
Okay, we would like to actually end with QA because we think it's very important. Alan and also Danny last week talked about some ways of doing the QA, but again, we want to emphasize how important it is and maybe what you can do. So, if I want to summarize, what would be the best way to QA the data, I would just say look at the data, sit at your desk and look at your data because your eyes are actually trained to capture any odd pattern that does not make sense. And your brain is actually smarter than the algorithms, the existing algorithms that are written to, again, capture outliers or artifact in the data. So I think we're still smarter than machines, and it's just a matter of again sitting and looking at the data and checking the data at every step and make sure that each step is what it's done on the data. It's what you're expecting it to do. So it's not because sometimes we think it's done the way that we think, but it's actually not in reality. Um, so I would say if you have time, check individual data sets and if possible at again every step just to make sure it's been done correctly. So here we just want to show you a few figures and like just to give you an idea to maybe you can use it in your data set. So for example, this is like individual from an individual subject, a PCC with a correlation map with a seat in PCC. So when we look at like maps, individual maps from individual subjects, if we know what to actually expect for, if we have some idea about the spatial pattern of the activation, that actually helps us a lot because then you can actually use your assumptions and judge whether what you have makes sense or not. So for example, like this should kind of be kind of close to default mode network map, but if I see something like odd, like if I see like half of the brain is positive and the other half is negative, then for sure there's something wrong with this data set or in the pre-processing step. Or if the alignment did not work, then your map is off, and when you put it on the underlay, there is no actually there's no good alignment. You can see that. So this is just a quick evaluation of each subject's individual map. But there are other things that can be done, just making sure that when you during the pre-processing everything was done correctly. So just to give you an idea here in this plot, there's actually a lot of information there, but I'll try to highlight some of them. For example, the first line is the frame-wise displacement. So this is a very valuable information, I think, because it gives you some idea about how the subject moved. You may have two subjects that both of them, let's say, they have 20% like bad time points based on some FD threshold. But I think it matters how these bad time points are distributed over time. For example, if subject number one, for example, had like most of the bad time points towards the end of the scan, maybe one option that you have is basically using the first chunk of your data, which is clean without motion. Whereas if your subject number two has that 20% bad time point throughout the scan, that might be harder to deal with, and you have to so looking at the summary information, like for example the percentage of the number of percentage of the bad time points is good, but it's more informative if you look at it, if you know the distribution and you know what happens, what it when it happens, and what its effect is on the fMRI signal intensity. So on the bottom row here we have the gray plot for the signal intensities, and you can actually align them and see like how the time series intensities change when there is motion or there are some other things. Again, that would be a quick way of actually evaluating your data at one glance. The second thing that you can check is basically the quality of your physiological recording, like your respiration and cardiac. So for this subject is looks okay to me, but if I go for example, for this subject, for example, it had lots of motion, and you can see actually the time series, the gray plot in the last row. You can see that the effect of motion in there. Then this plot, again, lots of motion, but in addition to motion, if you look at the third row from bottom, the respiratory recording, this recording is not considered good. It's actually a very bad recording because I believe the subject was alive and he or she was breathing, but you can see that the fluctuations are kind of tiny, like a kind of a flat line, and then it drops. So this is a bad recording. Then maybe this is not it's not a good idea to use this respiratory waveform and include it in the model. Yeah, this is a decision that, as you actually, again, if you look at your data, you will notice that, but if you don't and you let the code just compute your regressors, you won't you may not notice that actually later on. This is another plot that, again, if you look at the second row, is sorry, it's the cardiac recording. It may not be visible as you're looking, but if you pay actually some attention, there are some red dots actually in the middle of the time series, meaning that the peaks, so those red dots indicate the peaks of the waveform, so meaning that the algorithm failed in detecting the right peaks. So in this case, maybe you have to again go back, double check your parameters for that algorithm. If it's possible, fix it, but if it's not, then again you may just skip using like that cardiac waveform in your model. So again, to end this session, I would like again to emphasize how important it is to understand what actually the effect of each step on the data, and make sure that you do the QA early on, and don't wait until the end of the study, and don't wait until you're done with the group analysis, because then it may be late and maybe the results are caused by some outliers or something that it's not a true effect. That's all.